this course is Introduction to Computing, and in this course we are going to study how to use computers effectively for solving real-life problems that you will come across in your professional careers. As you know, in today's world, a computer is an invaluable tool to every engineer and scientist for solving problems related to his or her discipline. For example, if you are a civil engineer, you need a computer to compute the stresses on the various structures of a building. Or if you are going to be an aerospace engineer, then you might need to use a computer to compute the airflow around an aircraft. And so it's important for all of us to understand how to use computers effectively to solve our problems. And not just as users of computers, we need to be able to tell the computers how to solve our problems. So in this course, we are going to basically see how to use computers to effectively solve engineering problems. And as a first step, we are going to try and understand what a computer is, and at a very high level, what it does. Okay. So what is a computer? As the word suggests, it's something that computes. Well, in that case, how is it different from a simpler device that we are all familiar with, namely a calculator? A calculator calculates. So are the words calculate and compute any different? Well, let's try and consult a dictionary to find out. Here is what calculate means: to determine something by a mathematical process. And here is what the term compute means: to determine especially by mathematical means. So as you can see, the meanings of the two words are quite similar, and therefore one would expect a calculator to be similar to a computer, but it's actually not the case. A computer, as we're going to see very soon, is much more powerful, and we can use it in much more flexible and interesting ways than we can use a calculator. Okay, so we're now going to see what we can do using a calculator. This is something that is familiar to all of you. So let me show you a calculator. Okay, so here is what a standard calculator looks like. As you can see, it has buttons for various primitive arithmetic operations, and we can use these operations to do some calculations with numbers. For example, 56 into 23 is 1288. However, what we cannot use this calculator to do is to tell it how to combine these operations in a certain fashion so that a certain computation can be achieved. For example, how do I compute, let's say, the factorials of numbers using this calculator? You might say, oh, that's very easy. If I have to calculate the factorial of 5, here is what I'm going to do. 5 times 4 times 3 times 2, and that's 120, which is the factorial of 5, and that's correct. But you cannot teach this calculator how to compute the factorial of any given number. So for any specific given number, you can use this calculator to find the factorial by combining these operations in a certain way that you know, but you cannot teach this calculator how to combine these operations in some way so that it can compute the factorial of any number automatically. Well, you might say, if I want to do that, I can use a scientific calculator which has a primitive operation for factorial. But even with a scientific calculator, the set of operations that you have is fixed, and you still cannot tell it how to combine these operations automatically in a certain sequence so as to achieve a certain computation. Right? For example, your scientific calculator might have a button for factorial, but can you, for example, teach it to compute, let's say, the area of the intersection of two given circles? Well, you can't. And that's the important difference between a calculator and a computer. With a computer, you can actually tell it how to combine the various primitive operations that are available in a certain fashion so as to achieve the desired computation or to solve the desired problem. Okay, so let's look at some terminology now which relates to the concepts that we have been talking about. This instructing the computer about how to do a certain task is what is called as programming. I'm sure you have come across this term before. A program is nothing but the set of instructions that you are giving to the computer to carry out a certain task. And the third term is programmability, which is the ability of the computer to accept a set of instructions from you and to faithfully carry them out. And this programmability is what primarily distinguishes a computer from a calculator, because a computer is programmable, that is, we can give it a set of instructions to solve the problem of our choice, whereas we cannot program a calculator, or we cannot instruct it how to carry out a certain task. Of course, there are other important differences between computers and calculators, which are also significant. For example, a calculator can only deal with numbers, whereas a computer can deal with data in variety of forms, as some of you might be aware. For example, it can handle text, it can handle images, it can handle sound, and it can take its input from a variety of interesting input devices and so on. But the fundamental difference again is that a computer is programmable while a calculator is not. As I said, a program is the sequence of instructions that we supply to the computer in order to solve our problem at hand. There is a related term called an algorithm, which is similar to a program but different in certain details. So an algorithm is also a sequence of steps to solve a problem, but it's usually written in a natural language such as English and written precisely enough so as to be unambiguously understood by humans. A program, on the other hand, is essentially an algorithm translated to what is known as a programming language that a computer can understand and execute. So that's the fundamental difference between an algorithm and a program. You might think of an algorithm as a solution to a problem, whereas a program is the translation of that solution from English to a programming language that a computer can understand. In this course, we are going to talk both about how to develop algorithms for solving some simple problems, which you will find useful as building blocks for solving more complex problems. And at the same time, we are also going to see how to express these algorithms in a programming language and actually execute these programs on a computer. So let's now take an example. Let us say we stick to our old example of computing factorials, and we want to write an algorithm to compute the factorial of a given number n. Note that here n could be any number, and we don't know a priori what this number n is. So our sequence of steps, namely our algorithm to find the factorial of n, should be such that it can handle any given n and not just a specific n. So how do we go about finding such an algorithm? Well, we all know how to compute factorials. So as you know, the factorial of n is nothing but n times n minus 1 times n minus 2 times till 1, right? But how do I express this as an algorithm? Note that multiplication is fundamentally a binary operation, and we can really only multiply two numbers at a time, right? So how do we go about converting this knowledge of ours about the definition of a factorial into an algorithm for a factorial? Well, let's just think a little. As you can imagine, what we can do if we want to multiply numbers two at a time, we can start with 1. Let's call it for the time being as our result, and our n is whatever it is, and in each step, let us say we multiply result by the value of n. That's the first step. We multiply result by the value of n, and that will give us n, right? So let's take an example. Let's say n happens to be 5. So we start with the result as 1. In the first step, we multiply the value of result by the value of n, which gives us 5, and that's the new value of result. And in the next step, we have to multiply this result by 4, not 5. So therefore, we decrease the value of n by 1 and make it 4. And in the next step, we do the same thing, multiply result by the new value of n, and that gives us 20, decrease the value of n by 3, and we keep doing this. So in the next step, 20 becomes 60, n becomes 2, and in the next step 160 becomes 120, and n becomes 1. And how long do we keep doing this? As long as n is greater than 1. So once we have done this, we have essentially arrived at an algorithm to compute the factorial. All we need to do is to now express our thoughts more precisely. So here is the expression of our thoughts in the form of an algorithm. So here is the algorithm to compute the factorial of n. The first step is to read the value of n, and in the second step, as we did earlier while we were scribbling, set the result initially to 1. And as long as n is greater than 1, keep doing these two steps, and these two steps, as we have seen, are multiplying the value of result by the value of n and decreasing the value of n by 1. So set the new value of result to the old value of result times the value of n, and the second step is set the new value of n to the old value of n minus 1, and keep doing this, as you can see here, till as long as n is greater than 1. And once we are done, the value of result contains the answer to our problem, namely the value of n factorial, and we can output the value of the result. In this algorithm, right now we are not really bothered too much about where do I read this value of n from, or where do I print the value of the result, or how do I print the value of the result. That's not something that's bothering us right now. It is the steps 2, 3, 3.1 and 3.2 which are really important at this stage. Okay, and let's note some more things about this algorithm. Note that our instructions for computing the factorial of n is not just a straight line sequence of instructions to be executed by the computer one by one, but there are things which have to be repeatedly done. The steps 3.1 and 3.2 have to be repeatedly performed as long as a certain condition holds. This is called a loop in the technical jargon. The second thing that you should note is that we have to remember the results of intermediate computations. And the intermediate computations, as you can see in this particular simple example, are two, namely the value of result and the value of n. So these things, these values that you have to remember, these are called as variables. So in this example, there are two variables in this algorithm, result and n. I'm sure the notion of variables is familiar to you from your high school algebra, where you have equations like x plus y is equal to x square plus y square, something like this. But that mathematical notion of variables is very different from the programming notion of variables. In mathematics, variables such as x and y denote unknown but fixed values, whereas in an algorithm, variables denote values that may change over time. Okay, so as you can see, the values of result and n changed over time as we go through this algorithm and execute it step by step, and that's what the programming notion of a variable is. Okay, so let's now see this algorithm in action. So here is the same algorithm, and let's see step by step how it's going to execute and compute the desired result. Here's the first step. Read the value of n. Let's take an example, the same example as a matter of fact as before, and let's assume that the value of n that is given to us is 5. So this blue arrow indicates where in the execution we are currently. Right? So after having executed line number 1, we now have to execute line number 2, and the result of executing the line number 1 was that the value of n has become 5. Okay? So the second step is set the value of result to 1, and what do you think this will do? As you can imagine, this will do nothing but set the value of result to 1. Here it is. Now here is something, a sequence of steps which need to be repeated as long as a condition holds. So while n is greater than 1, do these sequence of steps. Well, this particular line in the algorithm is essentially just going to check whether or not n is greater than 1. The current value of n is 5, which certainly is greater than 1, and therefore the answer to this condition or the result of this condition is true, and therefore we are supposed to execute the steps 3.1 and 3.2. And because the condition evaluated to true, we have come to the step 3.1, which says set the new value of result to the old value of result times the value of n, and so the new value of result will be result times n, which is 5 times 1, which is 5, and that's what this line in the algorithm does. So the result becomes 5. Note that in this step n has not changed. In the next step, we're going to set the new value of n to the old value of n minus 1, which is 5 minus 1, namely 4. So we do that, and note that once we have finished executing 3.1 and 3.2, we must come back to line number 3 and check this condition again. Why? Because remember that the steps 3.1 and 3.2 have to be repeated as long as this condition holds. And this condition will not, as you can imagine, continue to hold forever, because in every step we are decreasing the value of n by 1, and therefore after some time, certainly after a finite number of steps, the value of n will become less than or equal to 1, at which time we'll stop repeating the steps 3.1 and 3.2, but at this point in time the value of n is still greater than 1, so we repeat the same steps. We come here, the value of result now becomes 20, 5 times 4, and now the value of n becomes 3. So we go back, n is still more than 1, and therefore we repeat the steps again. So result now becomes 60, and n now becomes 2, which is still greater than 1, so we do this once more. Result now becomes 120, the value of n becomes 1. Now when we test whether n is greater than 1 or not, we conclude that n is not greater than 1, because indeed n is equal to 1, and therefore this condition is no longer satisfied now. And therefore the steps 3.1 and 3.2 will not be executed now. We'll straight away come to step 4, which is to print the value of the result, and once we do that, the output is the value of the result, which of course is 120, and which of course, as you know, is the factorial of n. Okay, and we could have solved the same problem in other ways as well. For example, instead of multiplying 1 by n and then by n minus 1 and then by n minus 2, we could have started this process from the reverse direction, that is multiply 1 by 2 and then by 3 and then by 4 and so on. You could express that algorithm in a fashion similar to what we have done here, and I'll leave that as an exercise for you. And at the end of the lecture, there is one more exercise for you to try yourself. I want you to write an algorithm to compute the quotient and the remainder when a given integer x, which is more than or equal to 0, is divided by another given integer y, which is known to be greater than 0. So for example, if let's say 15 is divided by 7, then the quotient should be 2 and the remainder should be 1. But assume that only addition and subtraction are the arithmetic operations available to you. So please write an algorithm for doing that, just to reinforce the concepts that we have learned today. So before we end this lecture today, let me summarize what we have seen so far. We have seen the notions of programming, a program, and programmability. And this notion of programming and programmability is essentially, as we have seen, what gives a computer its power, because we can write programs to solve our problems and tell the computer to use these programs to find the results that we need. And before actually writing programs in programming languages that computers can understand, we have seen what the notion of an algorithm is, which is independent of any programming language, and we saw a simple algorithm to solve a simple problem, namely to find the factorial of a given number n, and we saw roughly how the computer would go about executing this algorithm.